Dr. D here, and today we're going to learn about where electrons are in specific elements. We will go through some quantum numbers and their associated orbitals to learn how to draw orbital diagrams and write electron configurations. And we will end with how we can use the periodic table to make this an easier task. So let's dive into it in content with content. So when first describing where electrons are, we should go through some quantum numbers. And we're going to go through four basic quantum numbers to begin with. We have the principal quantum number, represented by n, and it goes in a sequence of 1, 2, 3, and 4, so forth and so on. And this is used to describe the energy level, or an orbital size. Next up, we have the angular momentum, represented by L, showing a cursive L here so it's not confused with 1. And that'll go with 0 plus 1 each time, all the way up to n minus 1. And this will represent a orbital shape. Then we have the magnetic quantum number, represented by m subscript L, where it goes from negative L plus 1 all the way up to 0, and then plus 1 all the way up to L. And this will represent an orbital's orientation. Lastly, we have the spin quantum number, represented by m subscript S, and this is either going to be plus half or minus 1/2. And this will tell the direction of an electron's spin. So to begin with, let's go ahead and talk about the principal quantum number in a little bit more detail. Again, this is represented by n, and it goes starting at 1, going up plus 1 each time, and this will represent the energy level or orbital size. So one of the easiest ways to kind of look at this one is if we look at our periodic table. If we look at the very first row here, this is our principal quantum number of 1, which can be represented with a 1s orbital. Then if we go down one more row, this would be our principal quantum number equal to 2. So our first one that we would come across would be a 2s orbital, and you'll notice that this is much larger in size. Now, an orbital is just a probable space that you will be able to find an electron. It's a statistically favorable area for an electron to exist, about 90% of the time. Then if we go down one more row, we'll go down to the principal number equal to 3, and so it's now even larger for our 3s orbital. So the next quantum number I want us to talk about is the angular momentum quantum number, and this is represented by L. And this will go 0 plus 1 each time, all the way up to n minus 1. And this will tell us the orbital shape. So when L is equal to 0, this is representative of a s orbital, and the orbital has a spherical shape in nature. When L is equal to 1, this will be representative of p orbitals, which are kind of a dumbbell shape, if you will. Now, if we want to draw this out a little bit more freehand, I would end up drawing something that looks something like this, representing each of the 3 p orbitals, where you essentially can get by with drawing something that looks like a figure 8. Now, I do want you to kind of keep in mind that all these are existing all in the same space around the nucleus. And so if we combine all 3 of these p orbitals together, we'll end up with something that looks like this, which is somewhat spherical in nature. Spherical with some divots in it, if you would. So this is true for all of the different types of orbitals. When you combine them all, they all form something that looks roughly like a sphere with some maybe holes in them. So just kind of keep that in mind when we're talking about this. It needs to all be in 3-dimensional space all around the same nucleus. All right, so now for the more complicated ones, when we have L equal to 2, this is representative of our d orbitals. They kind of have a clover leaf shape, along with a donut over there. And then the last one I'm going to talk about is the when L equals 3, which is our f orbitals. And as you can see, these get pretty complicated pretty fast. All right, but again, this is just a depiction of the most likely regions to find an electron. So there's kind of a nice simple thing you can do with the periodic table. periodic table is actually arranged in such a way that these are kind of grouped together for these different orbitals. So if we look at the first two columns here, that'll be representative of our s orbitals, or when L equals 0, and this is referred to as the s block. When L is equal to 1, or we have our p orbitals, this is located in the p block, which is on the far right of the periodic table. And then if we go into the middle, where our transition metals are, we'll have L equals 2, which is our d orbitals, and this is called our d block. And then lastly, when L is equal to 3, we'll have our f orbitals, and this will be for our lanthanides and actinides. And this is known as the f block. And so as you can see, our periodic table is arranged in such a way that these are all kind of grouped together, and this may be useful later on. All right, so the next quantum number I want to talk about is the magnetic quantum number. This is represented by m subscript L, and it goes from negative L plus 1 each time all the way up to 0, and plus 1 again all the way up to positive L. And this is represents the orbital orientation. So let's take an example here where we have n is equal to 2. We'll have two angular momentums, one being 0 and one being 1. If we go down where L equals 0, we'll see that ML has to be 0. And this can be represented by a 2s orbital, 2 coming from the principal column number, the s coming from the angular momentum column number, L, and we only have one of those because we only have one possibility for our magnetic quantum number, or ML. Then if we look at our angular momentum quantum number equal to 1, or L equal to 1, we'll see this splits up into 3 different categories, where we have -1, 0, and +1. And this represents the different orientations we can have for our 2p orbitals. We'll have px, pz, and py. All right, and our last quantum number we want to talk about is the spin quantum number. This is represented by ms, and this is either going to be a +1/2 or -1/2, essentially representing what orientation our spin is of our electron. And so let's go with our last example we had earlier, where we have n equals 2. That'll split up into L equals 1, L equals 0, or L equals 1, and then we'll have our respective ML values. Now looking at the L equals 0, this can split up into 2 different possibilities for our spin quantum number of +1/2 or -1/2. And so if we were to represent this in a orbital diagram sense, we'd say we'd have a 2s orbital, and for the +1/2, we'd say it'd be spin up for our electron spin, and for the -1/2, we'd have a downspin for our electron. And we can do the same thing for each of the L equals 1. So we have 2 electrons in each one of our ML subcategories. And so if we want to write this as a orbital diagram, we have our 2p with 3 separate lines, one for each of our MLs, and then we can put in a spin up for each of our +1/2s and a spin down for each of our -1/2s. So these are our 4 quantum numbers we kind of went through, and there's a couple of rules that are involved with assigning these quantum numbers. One of the big rules is the Pauli Exclusion principle, which states that no 2 electrons can have all 4 quantum numbers be the same. So basically we can have 2 electrons that have the exact same 4 quantum numbers within a given element. So if we want to represent how these would look, we can use something called orbital diagrams. Now, orbital diagrams will be best shown here. So let's go through an example where we have hydrogen. Hydrogen has 1 proton, 1 electron. And so we're going to start off with a 1s orbital. We're going to start off with, we know that N will have to be equal to 1, which is our lowest energy state. L would have to be 0, ML would have to be 0, and then we have two options for our spin. It can be either plus half or minus 1/2. And so we'd have a 1s orbital that could have a spin up, or a 1s orbital with an electron of spin down. So either one of those would be acceptable. My normal convention that I go with is to do spin up first, but it can be either way. All right, then let's take a look at helium. Now helium has 2 protons and 2 electrons. So again, we'd be able to populate the lowest energy state first. So we'll have N equals 1. Our L would have to be 0. ML would have to be 0 as well. And then MS could be a plus 1/2 or minus 1/2. I'll just choose plus 1/2 for now. And then for our second electron, it'd be the exact same thing, but now our spin would be down. And so this would be best represented with an orbital diagram that would say 1s with a spin up and a spin down. So this is the orbital diagram of helium. Now there's a couple other rules with the orbital diagrams. We have the Aufbau principle, where each added electron occupies the lowest energy subshell. And basically what this means is the lowest energy state is what we're going to populate first with our electrons. So if we have an energy diagram here representing each of our orbitals, we start off with our 1s orbital, and then we're just concerned with the principal quantum number. This would be pretty straightforward, where we go up into higher numbers, and those will be at higher energies. So 2s, 3s, 4s, and 5s. But when we start adding in the angular quantum numbers and essentially the other quantum numbers, it gets a little bit more tricky. So if we look at our principal quantum number of 2, we could have S or P, and so we can represent the P here. Now the P orbitals are a little bit higher in energy than the S orbitals. Then we go up to the next energy level up. We have our 3s, 3p, and 3d. And again, P is going to be higher than S, but D is also going to be higher than P. And then we can do our fourth energy level, where we have 4s, 4p, 4d, and then 4f. And then finally we can have the fifth energy level with 5s, 5p, 5d, 5f. And there'd also be a 5g, but since there's no elements that actually have that, I'm going to exclude it from this list. So as you might be able to realize, it might be a little bit tricky to figure out which ones we need to fill up first. You may notice that the 3d orbitals are a little bit higher in energy than the 4s orbitals, but lower than the 4p orbitals. And the 4f orbitals are in between the 5p orbitals and the 5d orbitals. So it can get a little tricky with doing this. So there's a kind of a quick little check you can do to keep this straight without having an energy diagram. You can write down 1s being our lowest energy level, and then we're going to do the next energy level of 2. So that'd be a 2s and a 2p. Then for next energy level, that'd be 3s, 3p, 3d, and we'll just keep writing them in a list further down. So 4s, 4p, 4d, 4f, then 5s, 5p, 5d, 5f, and 5g. Now again, our current periodic table doesn't have anything in the 5g orbital range, so I'm going to go ahead and gray that out a little bit. Then we do our sixth energy level, 6s, 6p, 6d, 6f, and the G and H, also grayed out. And then the seventh energy level, our final row on the periodic table, which is 7s, 7p, 7d, 7f, and then G, H, and I. Again, grayed out since they're not actually used. So after you get this drawn on a piece of paper, then you can draw arrows diagonally down from the upper right-hand corner. And whatever it hits first, that is what you're going to fill up to begin with. So we'll start off with the 1s. Then we can draw another arrow, and then we'll fill up the 2s. Then we draw another arrow, we'll do 2p, then 3s. Draw another arrow, that'll be 3p, then 4s. And then another one, we get 3d, 4p, then 5s. And you can see this is following our energy diagram as well. It's just a handy little tool to kind of help keep things straight. Then we do 4d, 5p, 6s, then 4f, 5d, 6p, 7s, and then finally 5f, 6d, 7p. And we would do 8s next, but again, our current elements that we have in the world don't have that, so we're going to exclude it from that point on. All right, so another rule that we have is Hund's rule. The lowest energy configuration maximizes the multiplicity. Now what this really means is that we want to maximize parallel spin for degenerate orbitals. And basically we just want to make sure that for orbitals of the same energy, such as our p orbitals, we want to make sure that we have all of our electrons spinning in the same direction to help eliminate spin-spin repulsion. So let's go ahead and work through a couple examples here. So we have helium, where we'd have a 1s orbital, and since it has 2 electrons, we'll put in 2 electrons in there. Then let's move on to carbon, which has 6 protons and 6 electrons. So we're going to start off with our 1s orbital. We're going to fill that up. Then we'll go down to our 2s orbital, and we'll fill that up. So now we have 2 electrons remaining, and so now we have to go to the 2p. So we'll do our 2p orbitals, and we'll put in 1 electron for one of them. Now for our next electron, we want to maximize this spin. We want to maximize our multiplicity. So we're going to have them spin in the same direction, so we're going to go to another orbital and do the same spin we did earlier. So since we had to spin up, we'll do another spin up. Now both of these could be spin down, and that's fine, but you want to make sure they both have the exact same spin orientation. All right, so let's do another example with oxygen, where we have oxygen has 8 protons and 8 electrons. So we'll fill up our 1s orbital first, then we'll do our 2s orbital, and then we have 4 more electrons for our 2p orbital. So we'll put in one at a time, all with the same spin, and we have 1 more electron to put in here, so now we have to pair them up. So now we're going to put 1 electron as spin down in any of our p orbitals. All right, so let's do one more example. Let's look at iron. Iron has 26 protons and 26 electrons. And so we start off with 1s, fill that up, then 2s, fill that up, then 2p, and we'll fill those up all with the same spin to begin with, and then pair them up. Then we go to 3s, and we'll fill that up, then 3p, again, we want to fill them all up with the same spin to begin with, and then we'll pair them up. Then 4s, and then finally we get to 3d. And at this point we have 6 electrons remaining, so we're going to put 1 electron in each of the d orbitals with the exact same spin, and we have 1 more left over, so we'll have to pair one of those up. And so this would be the orbital diagram of iron. Now one thing to kind of note is that we have all these electrons with the same spin, and so if you ever have a bunch of orbitals with just 1 electron in it, all of them having the same spin, this is essentially what allows certain elements to have magnetic properties. So this is why iron is so magnetic. So drawing these diagrams out can be a little tedious, and so there's a kind of a shorthand way of doing this, and this is called electron configurations. And this is so you can just write out what the electron configuration is without having to draw a bunch of arrows and stuff. So both of them are pretty useful. This is just a little bit faster way to represent the same thing. So for helium, to write out the full electron configuration, we'd put in our orbital, which is 1s, and then the number of electrons within that orbital as a superscript. So it would be 1s2. Then for carbon, for the full electron configuration, we put down all of our orbitals we use, so 1s, 2s, and 2p, and then we put in how many electrons are in each of those. So our 1s has 2 electrons, our 2s has 2 electrons, and our 2p also has 2 electrons. Now there's a little bit faster way to write these out instead of doing the full electron configuration each time. You can essentially abbreviate it some by putting in a noble gas configuration that you've already used previously. So the noble gas that has the same electron configurations within carbon would be helium, because helium has a 1s2 electron configuration. So we can substitute helium in there, and then we just put in our valence electrons. So 2s2 and 2p2. So if you go up one row and look at that noble gas, that would be the noble gas configuration you want to use. And then you can just use your current row for the remaining bits. So for oxygen, our full electron configuration will be 1s2, 2s2, and 2p4, because we have 4 electrons in our 2p orbital. And the condensed form will look very similar, where we have noble gas configuration of helium, 2s2, and 2p4. And then finally we get to iron. And for iron, we'd have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. So you can kind of see for these larger elements, this is why we would want to use a condensed version, because most of the chemistry happens with the valence electrons. And so this has the same noble gas configuration as argon plus 4s2 and 3d6. So this is where the electrons would be that would actually have some reactions and chemistry and bonding that would occur for iron. All right, so there's a lot to keep straight here. We have all the column numbers, we have various rules to keep in mind, but there's kind of an easier way to go about doing this, and or at least I find it easier, and that's to use your periodic table. And so when you're using your periodic table, if we look at each row, that is going to be determining what principal column number you're on. So if we look at our first row, this is principal column number 1, so our 1s orbitals. And if we go down another row, this would be the principal column number of 2. So like our 2s orbitals and 2p orbitals. The other thing we can use is we can look at the various blocks. So we have the s block, which is the 2 leftmost columns. We have our p block, which is on the far right of the periodic table. We have our d block, which is in the middle, where our transition metals reside. And then we have our f block, which would be, in truth, between our s and d block on a true periodic table, but a lot of periodic tables go ahead and put it down on the bottom just to help save space. So using this knowledge, you want to make sure that one thing you kind of keep track of is that for your different rows, that is going to be whatever orbital you're in, with the exception for the D and F block. So for the D block, you're going to do your row number -1, and that's going to tell you what number to put in front of your D orbitals. So the first row that the D block starts on is row 4. So we do 4 - 1. That gives us 3. So our first one is going to be a 3D orbital for that series. And then for F, it's going to be the row -2. So the F block starts on row 6. So it would be 6 - 2, which is 4. So 4F would be our first F block orbital. So let's go through an example here. So let's look at phosphorus. Phosphorus has 15 protons and 15 electrons. And the easiest way to go about doing this is to just count out the elements. So I'm going to start off with hydrogen and work my way all the way up to phosphorus. So we have hydrogen, and that's going to be on the first row, so I know it's going to be a 1, and it's in the s block, so I know it's going to be an s. So it's going to be a 1s orbital, and we're going to put in our 1 electron, so I'm going to just do spin up, because that's what I like to do. And then we look at helium, so then that'll give us our downspin electron. Then we go to lithium. Now for lithium, we went to another row. So now this is going to be a 2, and it's in the s block, so it's going to be a 2s orbital. So I'm going to put an electron there, and then we'll go to beryllium, and we'll add another electron. Then we'll go over to boron, and this is where we're going to be adding in our 2p orbital. Then carbon, again, we want to make sure we're following the same rules, so we want to maximize our spin. So we'll put that in a separate p orbital with the same spin. Same thing with nitrogen. And then when we get to oxygen, we have to start pairing them up. So we'll add 1 there for oxygen, we'll add 1 for fluorine, and then we'll add 1 for neon. And now we're at a noble gas configuration, and that orbital is all filled up. So now we're going to go down to sodium. This is going to add a 3s orbital, then magnesium. Then when we get to aluminum, we'll have to add in a 3p orbital, then silicon, then phosphorus, then sulfur, So now we're at phosphorus, and so we got our electron configuration. So that's our orbital diagram for our electron configuration. That'd be 1s2, 2s2, 2p6, 3s2, and 3p3. And then for the condensed form, it'd just be the noble gas of neon. So we essentially go up one row and look to the far right, and that'll be our noble gas. And then we can add in our 3s2 and 3p3 for our current row of our current element. All right, let's do one more example. Let's do arsenic. All right, so arsenic has 33 protons and 33 electrons. So again, we're going to start off with hydrogen, and that would be our 1s orbital, then helium. Then we get to lithium, and that's going to give us our 2s electron. Then beryllium, then boron will be starting our 2p's, carbon, nitrogen, oxygen, fluorine, neon. Then we go down a row to sodium, starting our 3s orbital, magnesium, aluminum, starting our 3p, silicon, phosphorus, sulfur is when we have to start pairing them up again, chlorine, argon. Then we have to go down another row to potassium, starting our 4s, and then we go to calcium. And then when we start scandium, this will start our 3d orbitals. So we'll go scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. So now we filled up our 3d orbitals. Then we'll start with our 4p orbitals, and we'll have gallium, then germanium, and then finally we'll end on arsenic, which is our desired species. And so this is the orbital diagram for arsenic. We can write out the full electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p3. Or more likely you want to write out the condensed form, which is the argon gas electron configuration plus 4s2, 3d10, and 4p3. So hopefully you learned a little bit about the electrons and how they are positioned around atoms, looking at their orbital shapes, some about their quantum numbers, and then how we can kind of use orbital diagrams and electron configurations to have a better understanding of where the electrons are going to reside. So, as always, keep thinking, and I will see you next time. Goodbye.